Okay, for this video guys, we're going to be looking at what's called the divisibility proof by induction. Okay, so I'm just going to talk you through how this works. It's set up exactly the same way as the other one was set up. So we are asked to prove something. We write it in terms of P of n. We assume P of k is true. We then test pk plus 1. Okay, and then what we do is once it's all done and we've proven that that is the linkage, remember with the dominoes, that we proved that we got the link from one domino to another, we can then say that our original idea is true. So today what we're going to do is prove by induction that 3 to the power 2n minus 1 is divisible by 8. Now we could rewrite that if we wanted to, because 3 to the power of 2n is 3 squared to the power of n. So we could, if we wanted to, just turn around and say that this is the same as 3 squared to the n minus 1, which is equal to 3 squared, which is 9 to the n minus 1, and we're saying that that there is divisible by 8. So we could do that if we wanted to, and it'd be easier to do that. So our p of n then is, we're going to just use the whole idea that 9 to the power of n minus 1 is divisible by 8. Okay, minus 1 there should be there, shouldn't it? Yeah. Okay, so first thing we need to do is to check it. So let's put n is equal to 1 in here. So let's put p of 1 through here. If we get that, what you'll find is that we're going to get 9 to the power of 1 minus 1. And 9 to the power of 1 is 9. 9 minus 1 is 8. So what we end up with is that that there is true. Now if I'd asked you to do this early in your mathematical life, you probably then would have put 2 through, 3 through, 4 through, 5 through, etc. And you'd have kept going and saying it keeps working, therefore it works. However, we don't know if there's a number that might be very, very large that doesn't work for this. Say if we put n is equal to 1,000,000 in here, how do we know that that actually is still divisible by 8? We'd have to just work it out, and we'd have to keep going for an infinite number of numbers in order to prove it. So this is why we use induction, so that we only have to show that this will work for the first domino, link it to the second domino, which then links to the third domino, and so on and so forth. So that's why we use this method. Okay, so we're going to do what we did before. We're going to assume that pk is true, which means we're just going to change all the n's to the k. So we have pk here. We're going to say that what we have here is 9 to the k minus 1 is divisible by 8. And we could write this another way mathematically and say, well, that's the same as 9 to the k minus 1 must be equal to 8 times some number, which we're going to call a, where a has to be a member of the integer family. Okay. Also means that we can rearrange this, so we can say that 9 to the k is equal to 8a plus 1, and all I'm doing is I'm sending this minus 1 across to the other side. Now, the reason we're doing this, we're going to use this later, we're going to substitute this in later in order to prove this induction theory. Now, if you remember from the last one, we then had to work out p of k plus 1, where wherever we saw a k, we just put k plus 1 in. So what we're going to do here is exactly the same thing. So we're going to say that 9 to the k plus 1 minus 1 is divisible by 8. So is divisible by 8. Okay, so that's what we're showing, and we're going to try and prove that that's the case. Now we're assuming that this is true. We're assuming that this statement here is true, which means that this statement here is true. And all we're going to do is we can show that this statement is linked to this statement by the pk plus 1. Then we've essentially proven this by induction. So first thing I'm going to do is I'm going to break up this bit here, and you can see here that's going to be the same as, use my law of indices, that 9 to the k multiplied by 9 to the 1 minus 1. Okay, so you can see here that all I've done is I've broken this up, 9 to the k multiplied by 9 to the 1. Remember, when we multiply with the same index, we add the indices together, so that's what we end up with there at the moment. This is the clever part now, because I have 9 to the k here, look, we have it here, 8a plus 1, and I've got 9 to the k here. So what I'm going to do is I'm going to substitute this in for this. So if I do that, I get 8a plus 1, and it's multiplied by 9. The reason it's multiplied by 9 is this thing here, and then what I have is minus 1 from this bit here, which is the end of it there, yeah? So I'm going to try and prove that this is divisible by 8. So the next thing I'm going to do is I'm going to multiply it all out. So hopefully you can see that 9 by 8a is 72a, plus 9 minus 1. And I'm going to simplify that to get 72a plus 8. And then hopefully you can see there's a common factor of 8 that's going to come out here. So I'm going to get 8, and I'm going to get 9a plus 1. Now, as you can see here, because I've got an 8 in front of this bracket, what it means is that it must be divisible by 8. Therefore, we can say, hence pk plus 1 is true, assuming pk is true, and thus pn is true for all values of n, where n is a natural number. Okay, I'm going to do another one of them with you guys, just to show you that technique again, probably a little bit quicker than this next slide. Okay, so it's proved by induction that 3 is a factor of 7n plus 2 to the 2n plus 1 for all values of n. Okay, let's just tidy that up a little bit. 7 to the n, that's fine. We should be happy now that should be plus 2 squared to the power of n is 4 to the n. And then we've got the plus 1. Okay, so that's just tidying it up a bit. So that should be divisible by 3. Okay. Remember, if 3 is a factor, it's the same, it's divisible by 3. So p of n, what we're saying is 7 to the n plus 4 to the power of n plus 1 is divisible by 3. Nice and straightforward. So the first thing we need to do is stick a number in. So let's stick in n is equal to 1. It says for all natural numbers, so let's do p of 1. If we do that, we get 7 to the power of 1 plus 4 to the power of 1 plus 1. That gives us 12, I think. So that's equal to 12. And we can write 12 as 3 times 4. And because we've got the 3 in front of that bracket, that definitely works. It's definitely divisible. So next thing we do is assume that pk is true. So let's just write it like we did before. Just change all of the n's to k's. So pk. Okay. What we're saying is that 7 to the k plus 4 to the k plus 1 is divisible by 3, just like before. And that means that we can write it in a different way and say that 7 to the power of k plus 4 to the power of k plus 1 is equal to 3a, so 3 times something, a bit like this here, the 3 times the 4, 3 times something, where a has to be a member of the z family, yeah, so it's an integer. Okay, the next thing we do then is rearrange it. Now, I always rearrange it so that the biggest number, or the biggest power, or the biggest number here, so in this particular one, this here, okay, it doesn't really make any difference which way you rearrange it. You just need either 7 to the k or 4 to the k to be equal to something. So I'm going to say 7 to the k is equal to 3a minus 4k minus 1. So 3a minus 4 to the k minus 1. We now need to prove, okay, so now I need to prove the pk plus 1 bit. So wherever we see in the original here, wherever we see a k, we are going to put a k plus 1, and we're going to assume again that that's going to be divisible by 3. Okay, so we've got 7 to the k plus 1 plus 4 to the k plus 1 plus 1 is divisible. Okay, it's divisible by 3. Okay, so what we're going to do again is like we did before, we're going to break these up. Okay, the indices here. So my next line is going to be 7 to the k multiplied by 7 to the power of 1 plus 4 to the k multiplied by 4 to the power of 1, that's a k by the way, plus 1. Okay, and as we did before, what we're going to do is we are going to, wherever we see a 7 to the k here, we're going to put this 3a minus 4 to the k minus 1 in. So let's have a go at that there. So this here is going to change to this here. And you notice this multiplied by 7, so we're going to stick a 7 in front of the bracket. So what I have now is 7, and I've got 3a minus 4 to the power of k minus 1 plus, and we've got 4 here, 4 to the power of 1 multiplied by 4 to the k there, so that's 4 multiplied by 4 to the power of k, and then we have the plus 1 as well. Okay, so just run through that again. We've got 7 to the k is going to be changed for this, that's where this bracket comes from. The 7 to the 1 means we're doing 7 times that, which means 7 multiplied by this bracket here, which is this. Then have plus 4 to the k times 4 to the 1. Well, 4 to the power of 1 is 4, so we've got 4 times 4 to the k, and then the plus 1's all on its own. And now what we're going to do is we are going to multiply out that bracket like we did last time. If we do that, we get 21a minus 7 multiplied by 4 to the k minus 7 plus 4.4 to the k, or 4 times 4 to the k, plus 1. Now guys, this is not 7.4 to the k, it's 7 times 4 to the k. And likewise, this isn't 4.4 to the k or 4.4 to the k, it's 4 times 4 to the k. So let's collect everything we can together. So just the a's, we've got 21a. Okay, so that's fine. Let's have a look at the 4k's here. So you can see we have minus 7 lots of 4k plus 4 lots of 4k. So minus 7 plus 4 is minus 3 lots of 4k. And then we have minus 7 plus 1. Minus 7 plus 1 is minus 6. Okay, hopefully you can see that we can take out a common factor of 3. Hooray, which is what we're looking for. So a common factor of 3 is going to come out here. So 3. And we can take 7a minus 4 to the k. We've got minus 2 here. And likewise, just before, guys, you can see here we have the 3 in front of this bracket, which means that it's got to be divisible by 3. Thus, this is divisible by 3. And because pk plus 1 is true, assuming that pk is true, that means that pn is true for all values of